Hello, and this time we're looking at the double angle trig identities, and these are not them, these are the addition identities, and we did a video on that previously. So I'm going to use these to work out the double angle identities, okay? And then we'll go through a couple of examples of actually using them. So what is a double angle identity? It's when A equals B. So if these were the same angle, then this would become sine of 2a. And if that's the case, well then let's just write down what this would be. It would be sine of the first times cos of the second, which is the same, plus cos of the first sine of the second. And what you can see is that sine A cos A and cos A sine A are the same because multiplication is commutative. So sine of 2a actually equals 2 lots of sine A cos A. So that's nice and straightforward, nice little simple rule. Now cos is a little bit different. We'll come down here and give a bit more space for that. So cos of 2a, as A and B are the same, is cos of A times cos of the first times cos of the second, which of course the same, minus sine of the first, sine of the second, which are also the same. So we can rewrite that as cos squared A minus sine squared A. Now you see this one in 3 different forms, which can be quite useful because we can use the identity, I'll put it up here, sine squared x plus cos squared x equals 1. Okay, so we can substitute that in and we can get some different forms of this. So if we rearrange this to say that cos squared is 1 minus sine squared, we'd get 1 minus sine squared A minus another sine squared A. Or, to write that slightly better, it's the same as 1 minus 2 sine squared A. But we can also write it another way because we could substitute in what sine squared is, in which case we'd have cos squared A minus, and sine squared is 1 minus cos squared, so 1 minus cos squared. Well, if we get rid of that bracket, then we just have the 1 as minus and the cos as plus, or we can put the coses together and say that it's the same as 2 cos squared A minus 1. So hopefully you can see that there are 3 ways that we can write cos quite nicely, and it's important to remember these because if you ever trying to work some bits of trigonometry out, then often you end up with a squared that you need to turn into something like this, and you can do it with that identity, just cos squared becoming cos of 2a instead of squared, and that link between them is very helpful. Or the sine is also quite helpful, so good ones to remember and watch out for. Okay, now I'm going to have to do some destroying so that we can do the tan. I'm not sure, I can't really remember this one, so I'm not sure how much space it's going to take up, so I might have to delete the cos bit as well, but we'll see. So, same thing, tan of the first plus tan of the second, which is of course the same, minus 1 minus tan of the first tan of the second. And we can rewrite this, so tan A plus tan A, well, that's going to be 2 tan A, and tan A is of course tan squared A. So that's quite a nice little one to remember. I'm not sure if we can simplify that in any other way. This is of course a difference of 2 squares, so you could write it as 2 tan A, and then that's 1 plus tan A times 1 minus tan A. Now I'm not sure if that's helpful. It might be. There's no cancelling we can do there, but it might be that that is some vaguely helpful thing we can do. So now we know what they are, let's have a look at how we can use them in some examples. So here they are written out in much better handwriting than mine. Sine of 2a is 2 sine A cos A. Cos of 2a has 3 forms, cos squared A minus sine squared A, 2 cos squared A minus 1, and 1 minus 2 sine squared A. And tan 2a is 2 tan A over 1 minus tan squared A. So let's have some examples of these, see what happens. Write the following in their simplest form involving only one trigonometric function. Right, okay. Oh, well, this is diving straight into something very tricky here, because I've got cos squared of 3 theta minus sine squared of 3 theta. So this doesn't seem to be a double angle. There's a triple angle here. But anyway, let's see. Now, this is interesting because, look, cos squared a minus sine squared a. So this looks promising, doesn't it? Cos squared a minus sine squared a, this looks the same, would be cos of double that angle. The fact that angle is 3 theta doesn't matter. We've got it in the right form, haven't we? Cos squared minus sine squared. So we can write this as just cos of double the angle, which is 6 theta. So that was quite straightforward. 6 sine 2 theta cos 2 theta. Well, this looks familiar as well, because look, sine times cos. Okay, the A is 2 theta. When we mush this up here, we're going to make it into double the angle. So it's going to be sine of 4 theta. Right, okay, and if that's true, then we had a 2 here, yes? And we already had a 6, so 2 of that 6 has to come into the identity. So if we treated this as 3 times 2 sine 2 theta cos 2 theta, then you can see that this thing has become, with the double angle, has become this. It's lost the 2 because of that 2 there, but I've still got the 3. So it's 3 sine 4 theta. Okay, and then this is a tan. Well, I mean, this is nice and straightforward because it's very obviously tan. Now, I say it's very obvious. If you see this in the wild, as it were, if you had an integration question where it sort of integrates something like this, you might not instantly recognize it. So that's why it's important to keep these in your mind, so that you think, oh yes, tan of something over this. And of course, they might complicate it by having different numbers in front, like we did here. But this one's quite nice because it's 2, 1 minus tan squared. Yeah, it's all very nice and good. And we know that whatever this is, it will be tan of double the angle. Well, as it's theta over 2, this is just going to give us tan of theta. So that was a nice one. Okay, so they were quite straightforward. Let's hope they all work like this. Let's do another example. Find the possible values of sine theta when cos of 2 theta is this. Right, okay. Well, there's 2 ways to go about this. I suppose what you could do is you could just work out what theta was. You could do the inverse cos of 23 over 25, and you'll find various values, and then you'll then you'll be able to put them into sine. The problem with that is, 1, it might not be precise, and 2, yes, because we'll get lots of angles. I mean, it should work, but I don't think that's what they're expecting us to do. So I think we should try and do this with the trigonometry. Let's give it a go anyway. So cos of 2 theta. Well, this looks like this, doesn't it? So we could rewrite this. Now I just want it with sine. So let's rewrite it with this guy and say that cos of 2 theta equals this. Well, then 1 minus 2 sine squared of A equals 23 over 25. That seems fair. Okay, well, let's rearrange this and say that 2 sine squared A, so if we add that to this side and take that away, is 1 minus 23 over 25, which is 2 over 25. And then we can get rid of this 2, we can divide the 2, and that will give us that sine squared A is 1 over 25. And now this is looking quite plausible, isn't it? Because if that is sine squared, well, we can just square root both sides, and we can say that sine of A equals 1 over 5. Now, is that acceptable? I'm not sure that we can just leave it like that, because surely if it's squared, then it needs a plus or minus when we do that square root. So I'm pretty sure we'll need to put that in. It might be in the context of the question that we would lose that, but because we've done a square root, and it is perfectly possible for sine of an angle to come out as positive or negative 1/5, then I think we need that plus or minus there. So hopefully you can see how we can use these double angle things to take something, mush it into something else, and hopefully find our answer. Now, the issue you'll find is that with the double angles and with the addition formulae and with a lot of other trig identities that you might have to learn, there's a lot that you could make use of, and that's why these questions are more about experience than anything else. You've got to be able to look at it and think, oh, well, this looks like it might be to do with this, it might be that, and you'll only get that ability to sort of have a clue what's going on by doing lots of questions and struggling with them and then having a hint or looking up the answer and going, oh, right, that's what we should have done. And you've got to build up that library in your head of examples so that when you look at something you think, well, I know what to do with that. And sometimes they're really obvious, like, cos of 2 theta, well, that's a double angle straight away. You can see it's a double angle. Whereas this is harder to sort of think, oh, cos squared and sine squared. You've got to remember it the other way. You've got to not get confused by the 3 theta and remember that that is what a double angle becomes. So they are tricky, and it's about experience and doing enough examples until it's glued into your head. Anyway, if you have any questions about the example I've done there or a different one and you're not sure, then it can go in the comments. But otherwise, I'll say cheerio for now.